in this session, like, you can see this. We will see first wave of this going to be regarding that using this. I will explain what is the MATLAB code behind that. Like how to write the MATLAB code for that. Now you can check this. Like where in this thing, like for any coding expression, we will first write like what are the three variables we require. For the purpose, you can check this. Here I define the variables like n, that is number of subcarriers, within subcarriers. So even though we are having a total frequency, I divided that one into 64 parts. That is the meaning of this number of subcarriers. And after that, based on the number of subcarriers, one fourth of the like length, I'm adding a like prefix. So if you take that one fourth, so you get 16. That is the cyclic prefix length. Now, for analyzing this like waveforms, that I assume that I consider the sampling frequency is 10 kilohertz. That means whenever like always the sampling frequency must be higher than like, at least twice higher than the measurable frequency. Now after that, you need to consider how many number of symbols you want to translate. Here, but I consider only 100 symbols. You get more number of symbols means like the delay to run the system it will take some time. So for that purpose only to reduce the latency, like I use less number of symbols. And in this I used four form modulation technique. You have seen the previous one. Now you can check this. For finding the bigger rate one, you have the signal to noise ratio 0 to 30 resistance of 5. Now, this is now our reaction like a going to become will generate. Now we can check this like how like first thing in this black diagram, if you remember me. But first thing is to generate the data. How we are generating that data? Everyone knows that based upon the number of symbols, like we will generate this random data. Here this random data is in terms of zeros and ones. Now, like with the help of this number of symbols and frame size, we are generating that data. So once we are generating that data, now we need to like as a part of second block, we need to map those bits into corresponding symbols. So we can check this. That means now with the help of four-form modulation scheme, we are mapping those symbols. So after that, these symbols like this is what we use this command. Like we after we reach a command. Like after we mapping, like people know this mapping, how you will do this mapping and all. Like after that, like this actual with the modulation. That means that after mapping the symbols, we need to apply OFDM modulator on the symbols. So OFDM modulator is nothing but simply your IFFT, like inverse fast Fourier transform. But see, sometimes some people they will use IDFT. The main difference between this DFT and FFT is in terms of processing speed. So DFT usually is somewhat complex and compared to this FFT. That is the reason we will prefer FFT. Now, now these symbols, like what is the data we are having, we will apply inverse fast Fourier transform on the data. Now that data now it becomes like we will convert the data into time domain. Like up to now we are having data in frequency domain. By applying IFFT with the help of command like FF tactical group signal. So you get the result in terms of time domain. Like so now we got the result like data in time domain. After what happens means you can observe this. Once data is converted in time domain, after this, there is a problem of maybe intersymbol interference. So to avoid that intersymbol interference, we will add some part of data, that means some weights from the Thailand, we will take some weights and we will prepare it, we will prefix it. That is nothing but cycle prefix. For that, in this code we use 16 weights. Now, once we are adding the cycle prefix, that data we are transmitted over the A. Now we can check this channel. Now, this is the one modulation data. So check this. Now, once the modulation over, that data I have transmitted over the channel. Clearly, you can see this here. I consider end white Gaussian noise. Like everyone knows this Gaussian parts. That one, like in reality, like in ideal case, we will consider this Ederian channel. But in reality, we can consider like any frequency like IW channels, like extended vehicle channels, type A, type B, type C. Or we can consider like prediction channels. We can consider like in real double dispersive channels. Those channels we can consider. But first of all, once we know the ideal case, then only we can go to the practical one. And for that reason only here we consider Ederian channel. So we consider Ederian once we are transmitting the data over the air means there is a chance of adding noise in the channel. So that is the reason only we are adding that noise also, that is Ederian noise. So once we are adding this noise, we will get some data. That is, whatever the data we are getting, that is the first step at the receiver end. So once we receive that data, that is, we can check this, that is the received data. Now, as part of demodulation, first what we will do means, we will do beam connect. First we will map that one, like converting from that one from analog to digital converter. Later what we will do means that one once we are converting that one, we will apply like serial to parallel conversion we will do command. Once we are doing like converting from serial to parallel, now this is entirely the data is in time domain. So to convert again to frequency domain, I used FFT here. So while applying FFT operation, that is, you can check FFT of received data with respect to any number of subcarriers. You will get the actual one, like the signal in frequency domain. Now again, we need to demap. Like usually we use UPSC symbols. Like in CMV, we need to reverse it. So for that purpose only we use PSK demodulation. Again, using like 4 form at UPSC. For that purpose only, we know that in constellation mapping. So constellation mapping, suppose if we are using 4 form means we need to divide this entire circle, that is 180 degrees radius by 4. Suppose if you are taking maybe 3 6 like 16 form means you need to divide that one with 16. So in that case, we'll like the 16 form means. Now what happened means you can check this. Now we are converting the symbols from decimal to the binary case. Once we are converting with that, again we will convert into the serial case. That is, we did vectorization. Once we are doing that one, like we will compare the actual transmitted data and this received data. Now we can check these. Like based upon this number of various bits, we will decide that how much information we are receiving error. So if you check this clearly, like here I am running this code, you can verify this. But check the result. Like if you observe this one, check the first one, that is what like we transmit like transmitted coefficient signal in time domain. There for like exact analysis, I consider 8,000 samples. So these are having their amplitudes. That is actual traction verb in the first one. In the second graph, it tells you what is the received signal we received. Again, received signal means may include noise also. So now we need to differentiate. We need to understand how many bits we are receiving error. So if you observe the below plot, like third one, you can check these. That is the original and received one. The original one is like highlighted in red color, and the received one highlighted in blue color. So errors means those values. So this is about OFDM, how we will do that. Now if you go to the objectives, but this is the one of the major work that is more tables. This is what I concentrated previous also. So here since what is this is in multi-carrier, we are having PF is one of the major issue. So to explain that one only, here we draw the power levels and what is the complementary unit distribution of PAPR. Now we can check here. Here I consider for this case, the first scenario, the number of Dopplers are 60, that is divided with n. Number of delay beams I consider 32. The modulation used here is QPSK, or nothing but 4 form. Now you can check this. Now after that, we have converted the modulation. Like if you want like 4 means to represent those bits, you require 2 bits. So for that purpose, I converted like in terms of bits. So everyone knows that is log 2 modulation. We will use the formula like log 2 m. So after that, we are trying to generate the frames. How we are generating that frames is nothing but multiplying the number of delays with Doppler waves. That is NPM. After that, we are generating symbols. Suppose if you want the number of bits means we are converting like symbols into bits. That is, whatever the number of symbols we are having per frame is multiplied with number of bits. That is what that one, and into m bits. I already mentioned the number of frames considered here is 100 for simplicity. You can take any number of frames you want. First, like this example, I consider this. Again, after getting this result, we can extend to another scenario also. Check this. Here, I consider real-time channel, that is delay Doppler channel, with number of like I consider number of reflectors are only 4 parts. So that means we will get number of taps, like for instance is 4. So delay taps 4, Doppler taps 4. So maximum length you will get 4 means 0 to 4 means you will get 3. 0, 1, 2, 3. Now like these are nothing but like various in campaign taking we are having those values gamma mu and all. Like this Ni1, Ni2, Ni3 and Nim. These are initialization of that one. Maybe like I will express that one in actual code. Like next one is like there is power, like how much power we will receive. For that purpose will I initialize here. After that power of compounding one technique, technically like that. So those are actually initialization of variables, like how we will do in remaining also. Now we can check this. Now we will go to the actual one. What you observe is the first step in case of OFDM and here or any modulation technique, in general this is true. So always we will transmit, like means we will generate the data by using some random command. So here I generate the random sequence. So once we are generating that sequence in OTFS, we will keep that data into the delayed Doppler domain. How we are placing these symbols in delayed Doppler domain? To observe like previous example, clearly if your user equipment is moving towards base station, In that case, we will consider it as it is having some positive Doppler shift. If the vehicle is moving away from the base station, that means it means we will consider as a negative one. Again, the strength of the path depends upon where the vehicle is, where the reflectors are. Now we can check the second one. We are like assuming the temporary data. Why? Because means whatever the data we are generating random sequence, that is not fixed. If you are iterating now, you get some data. Again, if you are taking one more time enter, you get some other one. So that is the purpose of the I get data temper. That means temporary data. So that data we are converting in terms of decimal values. So after what it means, I map with the help of form modulation technique. Here, like I mentioned, as mentioned, here I consider four forms. So now whatever the data we are having, like 100 and all, those map in terms of 1 plus 0 like that. So once we are converting the data in like data in serial, we will map that one with the help of reshape, we will convert it into matrix form. So that is nothing, is nothing but delayed overview. So now the first step is over. What it means? We are keeping information symbols in delayed overview. That is the first task of 40 Now you can check this. So that is the main difference between OTFS and OFDM. If you remember the previous block, this keeping the information symbols up to the delayed Doppler domain. That is the only novelty between this OTFS and the existing OFDM. Now, what we will do means, now these are symbols that are available in delayed Doppler grid. Now, our task is to convert that delayed Doppler domain information into time domain information. Further, we are having two options. We can convert directly by using jar command or jar transformation. But if we directly convert that one jar transforms, that is sometimes we may get more errors. So instead of what we will do means we will follow two-step approach. So two-step approach means you can see first this code, you get some idea. That means now with the help of inverse symmetric final Fourier transform, we convert the data from delayed Doppler to the time frequency. That means first we are applying FFT on the columns of the data that is across the delay. Then after we apply inverse first Fourier transform on entirety. That means even though we are having delayed Doppler gate, first we apply across delays after we apply across Dopplers. That is nothing but FFT of the data. The entire data we applied for IFFT. Now, this is nothing but again, if you observe means it is again two-dimensional data. That is inverse symmetric Fourier transform. But our agenda is to transform the data from 2D to 1D. That is especially from what is the domain we are having data. That one we need to convert to the time domain. So now with the help of ISFFT, we convert the data from delayed Doppler to the time frequency domain. Now, now we need to apply the generalized version of coefficient modulator. That is nothing but Heisenberg transform. See, what is this Heisenberg transform means? It is simply your IFFT operation on the previous block. So, if you apply IFFT of this Heisenberg symmetric fast Fourier transform, you will get the data in terms of delay time. So there time is nothing but the number of delay pins. Now what we did means now it is the result is in terms of after this Heisenberg transform, we got the result in terms of delay time domain. But we want the result in only time. For that purpose, we did the vectorization. So therefore vectorization we are converting from matrix to vector. Now once we are converting this, that actually we can send the data now. But what happens means the data actually whatever data we are having up to that S, that data is having some high peaks. So if you are having 5 pixels your data means this that means your amplifier or amplifier need to be operating in non-linear region. So because of that we are not getting proper results. So always we need to operate our power amplifier in linear region. So for that purpose only we need to reduce the strength of the actual transfer signal. So in order to reduce the strength of the signal, we will apply compounding. But before that, maybe there is maybe chance of first symbol maybe interface with second one. So to eliminate that one only we have added this cycle prefix. Clearly you can check in this code how we have added the cycle prefix means the type part of your original sequence, some part of your trial sequence are appended to the actual one. Now once we are adding that one, we apply our companion one. So this is about our transmitted part. Now we can check the companion one. So here we can insert three compounding techniques. One is error function compounding, another one is log root compounding technique, another one is generalized one, that is normalized singular compounding. Just to observe the variables named. The first one is SCP, like the first one SCO is error function of absolute value of CO, SCP. Here SCP means cyclic prefix version of your actual transmitted data. So that is your transmitted data now. For that purpose, that one we need to find what is the normalized one. The normalized coefficient, like mentioned that one I use alpha. Like everyone knows this is the formula, like the mean value. So it is the square root of the mean value of actual data to the total data. Actual data means your OTFS. Total means compounded version also we need to include it. There is nothing but normalized one. Now this entire this normalized coefficient we are multiplying with actual compounding and distribute like over a long distance purpose. We use like sine one also. That is SIN means signal function. So that data like XU1 we are now like is ready to translate. That is related to error function compounding. The second one is logarithm compounding. This is another compounding technique. Like if we have some mathematical, like everyone knows this, if we have some mathematical information regarding compounding, we can apply that one. Like there is beta is nothing but normalized coefficient. Now coming to the third one, that is already known one to everyone, that is mu. Mu SCP means transfer data. Mu means what is the compounding level we need to take. Now this is actually these are compounding techniques, three compounding techniques. Now we're trying to find what is the PA values, like how to find peak values. Let's check for one case. Remaining case also very similar to these. The first one is without compounding. Like we need to check first of all what about our transmitted signal. So the experiment is nothing but whatever data we are having for that one, we will find the magnitude. It is nothing but observed value. So after that, we need to do like the square of that one. For that purpose, like taking the instant power is nothing but square of that magnitude. So after that, we need to find mean value. Mean square value is nothing but mean of that magnitude of data. Similarly, you know this, what is the peak value? How to find peak means maximum of that one x magnitude square. For remaining things, like everyone knows this, that PAPR means is the ratio of peak power to the average power. So we are finding the peak value as well as mean square value. And if we are dividing that one, the peak value to mean square value means you will get peak to average power ratio for each frame. Now, similarly, we need to find, like, want to find instantaneous average power ratio means that is nothing but instant power to the, that means instant power means each frame they are having some power. We will find that is nothing but instant power. Like instant power to like means my value means instant average power ratio. Now whatever we will convert that one, we convert that one into in terms of plots. That is the actual code. After that we are converting in terms of dB. That is dB scale. For that purpose only power no. That's why we are using 10. 10 after the higher pair of symbol. Again, if you want to see the histogram plot, we can apply each command for that one. After that, we can add like my NI one is nothing but we observe that one we are initial that is zeros. We are adding this NI. Again, for this one, we want to know what is the peak power for this. Like this frame, how much peak power we are having. Again, what is the peak value? Similarly, we are finding what is the average power means by. If you observe this, check this. Like it is very similar to the like uncompounded one. Compounded one means like this is some notation. Like both are same. Like we are extended to uncompounded to compounded one. Here variables may change, but the procedure and everything is same. Variables cunning, but these are like normal procedures. Now we can check this plot. How we draw the plot. Here we have symbols. If you want to check means like to convert to normal scale to large scale. I apply this formula. Behavior of symbol dB means 10 times log of behavior symbol. So I would like to know what is the histogram plot. For that purpose, I take an histogram of that behavior symbol dB. So what is the minimum value and what is the maximum value and which steps are required. That also we can vary. So that one, like whatever we did for at like without compounding case, we did for compounding also. That is case one is for error function, second one for some log compounding, third one we applied nothing but Mula. Like we can check the results. Like with respect to results, we can talk more. Like here, like as I said, we measured what is the system of behavior and what is the peak and average values. Now check the power levels for these combined techniques. The first one is indicates the normal signal, that means without compounding, that is ODFS signal. The x-axis indicates the number of samples, y-axis indicates the power level. That is first one is indicates normal one. Second one is indicates that is green one indicates error function combining one. Now we can check the amplitudes. Like the time axis, everything is same, but we need to observe what is the peak values and what is the lowest values. So if you observe this is having somewhat better when compared to the actual one. The same thing I applied for error function compounding, that is green one. After log root compounding, that is mentioned in red color. Pink one, like I applied for Mula one. These are the power levels. Like you can check this in all three or four scenarios. The average power is same. That means that is first plot is without compounding, remain three are compounding. So irrespective of like, what modulation technique or what is the compounding you apply, the average power is remains same. How we are getting that average power remains same means by doing the normalization for compounding. So if the average power is remains same means then we are eligible to find what is the bit error rate. Now the average power is remains same means Now we can check what is the peak values. Now again I am speaking these power levels are with respect to single frame. So that means this power levels will vary with respect to frame to frame. That means we cannot change our campaigning with single result, like single frame. So for that purpose, what we will do means, like in order to analyze, like in order to know our proposed one, we cannot say with respect to single frame. For that purpose, what we will do means, we will find for multiple number of independent frames. In this one, I consider 10,000 independent frames. You can check that. This is the result we got. But this is nothing but like complementary cumulative distribution function of PAPR. So in this we can observe this. The black one indicates the traditional PODP signal is having that much 50 hours power ratio. Now the red one indicates Mueller compounded one. Now we can observe that when compared to black one, like this Mueller giving better direction. Now after that, the green one indicates our log root compound technique. So log root, that means in this work we propose two techniques. One is log root compounding, another one is error function compounding. So when compared to Mula is given red color. This green one, that is nothing but our log root compounding, provides around 1 dB reduction of PAPR. You can clearly see this. So you will get around 1 dB, but when compared to the actual voltage signal, it is more gap, it is around 4 dB. That means even though we are having this Mula compounding, observe this, we are getting 1 dB of production of PAPI. Now, if you take one more compounding, that means we applied one more, that is last root compounding. That's what we got when compared to. Next one is error function. Error function is giving more reduction of PAPR than log root and mu log. That one is highlighted in violet color. That means out of these three, we actually propose only to error log root compounding. So error function compounding provides good reduction of PP average power ratio. Now this is the final code, you can check. Now in this case, like our main intention like in this work is like again we need to reduce the PAPR. For that purpose, I implement like we are taken with the help of what we say like AI tools. Here what is the algorithm I used to mean auto encoder. Like everyone knows this auto encoder. It is having some steps in it, like actual data, rectified linear unit. Everyone knows that stages. Now you can check this. But again, insulation is same, like without like deep learning techniques or normal techniques. Everything is same, except that algorithm you can check this. Up to this part, you can check this, like insulation of all parameters, n values, modulation order. Here I consider the number of symbols. That means we need to train to the system. So for that purpose, I consider more number of symbols, 10,000 symbols. Now after that, we need to like tolerate how much value we can tolerate. I take in 10% of tolerance, that is 0.1 value, 1. That means now each iteration, how many epochs? Completion of one iteration is nothing but epoch. Here I consider 20 epochs. For each epoch, I consider 64 batches. Like learning rate is 0.01. This is the installation of parameters. Now check the generated training data. My first step is like conventional same in here also same. So we generate some random sequence based upon the modulation order and a number of symbols. So always know this, there is in terms of ones and zeros. Then what we did means when like these symbols, the first is we need to train. So how we are training and that we can check that we are like with the help of QBS modulation symbols we given train. Again here in case of autoencoder, actually we are having data in terms of complex. But this autoencoder we need to apply like real values are different and images separately. So for that reason, I am taking like real values different and imaginary values are different. Once we are converting that whatever that we are having into real and imaginary, that course I am using this the target one. So once we are getting that data is given to the autoencoder. Now you can check this. These are the number of layers in this autoencoder. Input layers. Now we are having various rectified linear layers. Here I am considering only three for analysis. But to be frank, everyone knows this autoencoder, like as the level of progress, as rectified linear is going and adding means, the dimensionality of data will be reduced in image processing. But here what happens means, in the first stage we are having various peaks, like it is having maybe some less peaks, high peaks, what other peaks we are having. So when we are using this rectified linear, like reconnector layer, like we are taking like 256, like you can check there is a one. Now, by applying rectified linear way, we can reduce the dimensional. That means we can compress the high peaks to some value. Like if that compression is not enough for means, we will take one more rectified linear. After what happens means, again the peak. Suppose the peak is maybe 10 watts. If you apply this rectified linear, at least some of the samples may be reduced to some value, maybe 10 watts to maybe 9 watts. After what happens, suppose if the direction of the we will measure peak average population. If this is not like 4 amp is not tolerant means we need to take one more. So by adding up to what we will achieve means now initially we are having 10 volts is the maximum one. Now by adding this critical linears one by one, it will be compressed. That means maybe next step maybe 9, maybe after that maybe 8 like it will compress. Now is it good to compress up to like our target? So that is entirely depends upon what data we are giving. If we are trying to compress data from like 10 watts to maybe 5 watts means, we observe that if we are compressing means at least some pieces we are missing. But in reality, in our communication, if you are talking with PA means we need to reduce the peaks. So this process what happens means if you are compressing signal further and further means there is a possibility of adding more noise. So we need to check where the noise is adding. So because of that what happens means the noise that means if your strength of signal is reducing means noise will dominate. So we need to check that one. Then since we are trying to find only peak to average power ratio, so only the transmitter and all I explained this. So this is the data encoded the transmitter end. At the receiver end, we want to find the bit rate that is exact replica. Now, now we need to go for training stage. There is the installation of those. Again, if you have some idea in machine learning, we know that we will take like we will talk with respect to number of epochs and what is the batch size. So you can check this. First we will generate what is batch size. After that, once we are taking one batch size, that one we will give it to the training stage. That means the training stage means vertical linearity unit stage one we will give. If you are not satisfied that compression means we will give to another one. So in that way I consider two stages. After the DL FEL is deep learning toolbox. So suppose we are having deep learning toolbox, then only we can use the command. Otherwise, it will show some error. So with that, So if we are having deep learning toolbox means like communication tool also we are having some applications. So therefore that deep learning future values I found out. So after that we are taking Adam. Our batch is we are taking the help of Adam optimizer. So that is Adam his name. So after that I am integrated for 20. You can check that. Now, once we are giving training, that means for the system, we are given training up to 10,000 symbols. Once we are given the symbols, then we need to test. That means, suppose you are writing the program multiple times, next time you are automatically whether you are able to write or not. Like that, we need to like once we are giving the training for system, we need to test whether it is classifying properly or not. So for the testing purpose, I consider 500 symbols. So again, I am taking these symbols up with the help of these testing bits. Like we'll try to like extract the features from this. That means each person has some features. With the features, what is the data we are already trying to see them. So we are that means figure out what are the features. Data is classified. So you can check this now. Output or output is in terms of you get only real data. So but again our actual data back means we need to find complex data. So for that purpose I applied complex for that data. Once we are applying the complex data, we know that how to find this average values. That is, first we need to find what is the original data. Then we will take the encrypted one. That means encrypted means after applying depending toolbox, that means how much values we are reducing. So for this, like you know this, how to find this peak values. This is what everyone knows. If you are taking the maximum of your data, that means you get peak value. The mean of your observed value square means you will get average square, like the ratio of peak to average is nothing but original one. Next one you can check below one is like encrypted one. Encryption one you can check the formula is same. Now we need to test what is the like system of behavior we are getting. For see, with the help of deep learning, you can get better prediction of behavior. Like even we cannot assume that. Now check the command window that is visible means. Here, like each epoch is considering like batch sizes, how much loss we are getting. If we are considering only 20 epochs, like you can observe like what is the batch that is running, how much loss we are getting each epoch. But for analysis, I consider only 20 epochs. Actually, this work is accelerated aggregate transactions of communications with a simple one. He just applied autoencoder. He got transaction paper. This is done by V. Wang from Southern University of Science and Technology, China. This is not our paper, but we take that paper and we analyze that. You can see this graph like even like how we got initially. But really, initially by seeing that results in that paper, I thought it is somewhat maybe not genuine. But what happened means actually, if you observe stage by stage, like here I added only two stages. If your data is even noisy data also, if you apply machine learning technique, we are getting clean version. How we are getting that clean version means based upon futures. Like it is clearly like again, if we are giving less number of samples for training means we are not getting that much good results. You need to train your system like by keeping more number of values. Suppose if you are giving some less values to train means by testing you will not get this result. Surely. So whenever you are training more number of bits, getting like we test small like this number of bits means in that case you can get this. We can see clearly the red one indicates actual wave signal. So if you observe actual wave signal, it is PF is up to 10 dB. It is a 10 power minus 0. Now you can check by applying autoencoder, it is reduced. It is not even 0.5, it is around 0.3 like that. So this means reduction is really possible. So that is the reason sometimes in transaction you cannot judge like it's true or false. But if you implement that part, you know that whether it's proper or not. So that's what we tested. We got this result. Like again, we extended this part. Like this is the autoencoder based OFDM. Actually, my team, like under me, some scholars are there. They are working on AFDM, different frequency video multiplexing. Recently, like 1 month back, we got one paper like 90 access. Like one more is that is based upon this normal technique. We applied autoencoder for AFDM. That is like we got some minor review in IEEE transactions of regular technology. Like one more paper, like based upon like we assume that like PAPR is one of the variable. Based upon that, with the help of probability theory, we find some moments like moment one, like what is this, all those things, mean variance, all those things we found, and that method we submitted wireless letter. We are expecting that we get some good like outcomes based upon this autoencoder. But if you come to this machine learning, like we mainly use for reducing high peaks or damage reduction means we will use autoencoder. Before that, most of the people what they use means principal component analysis. But what is the drawback of the principal component analysis when compared to autoencoder means? In case of principal component analysis, we will not keep all the features. That means we may lose some edge information, like we may lose some high peak values information amplitude. But with the help of auto encoder, we can preserve and we can find all each and every point. Because of that reason only, when compared to principal component analysis, this auto encoder gives like good result. We will expect some more like if someone is interested towards maybe like machine learning and is interested in wireless communication means we can implement these deep learning techniques. Again, if you are speaking strictly means autoencoder comes under neural networks. That means what is the data we will give as input, we will not train that. That means we will not give the label. That means suppose if we take supervised learning, we know what is the input and what is the output. That means we are giving the labels. But when compared this autoencoder is unsupervised learning, we know inputs, that's it. We don't know what is the output. So this one is autoencoder mainly used to classify whether it is suppose we take some example, email. Some like if you check means you get actual emails, spam email. That is classified again based upon unsupervised learning. In this unsupervised learning, like auto input is one of the example. Suppose if there is some abnormalities present in our body also means, like suppose you take some small child is going for LKG or nursery, you don't know what with the help of what disease suffering, like what is the issue. But if you use this unsupervised learning, we can find the abnormalities of the person also. So if you are aware this like this machine learning tools like how to classify and all, like we need to use supervised and unsupervised learning. or you need to use this auto encoder, you can find various applications. Suppose if you are like anyone is interested like towards this wireless communication means I'm very happy to help you. Again, see I use here for MATLAB coding. If you are expert in Python, that is very simple. You can solve like you can write the entire code. Like you have conversion tools are there. Suppose nowadays ChatGPT, like everyone knows that tool. With the help of that tool also, you can write the code, but you don't depend 100% on that. My smart. Okay. Like these are three results that I would like to give. Actually, having the code on the AFTM, but that is under consideration of transactions. I cannot give. So if you have any queries regarding this, I'm happy to help you. Like any queries or any work we are doing.
Participant, do you have any questions?
I ask at least one, like, you have, right, QPSK compounding. Yes. Sir, actually, the implementation is very simple, sir. Like once we know auto encode structure, it is having some layers. Like we know, right? Like from dimensional, like if you know what is the number of stages, like critical unit, activation layer, later space. So activation layer having idealization, right? So exactly what edit means? There are some people that are working image processing to reduce the dimensionality. There they use dimensional reduction. Here I am just of that same taking I reduce the peaks. What I did means I taking this activation layer with all actual signal. After if I apply rectified linear unit, I got some reduction of the peaks. So stage is going at that means I use one more rectified linear unit, peaks are reduced further. Again, we cannot use more number of rectified units. If you are using means the dimension is reducing further and further. But if reducing further and further, the noise effect also comes in the picture. That is the reason we need to consider, like we need to understand how much you can maintain, how much layers you can consider. Yes, sir. Number of layers are increased means the strength of signal is reduced. But if the strength of signal is reducing further means the noise will play a crucial role. That is the main reason based upon our requirement. Like our again, if we compress further and further, you will get better bit error rate, peak to average power ratio. But when it comes to bit error rate, we are compressing means we are disrupting the actual transmit signal, right? See, whatever signal we need to transmit, we are not transmitting. We are compressing that signal, right? That's what. If we are compressing means again we need to expand at the receiver end. So during this compression expansion, there is a chance of adding noise here also. The levels will change. So because of that, you will get more errors. So if you are reducing the behavior means we need to take care about other parameter bigger. We need to make it always spread up things. Like again, in our requirement, we need to focus on behavior or bigger.
Okay, now we can. కన్సర్న్ లెటర్ అడిగాడు అది ఈ రెండు పంపించాల్సిన అవసరం లేదు. ఒకటే ఉన్నాయి. ఇప్పుడు వాడు జర్నల్ ఏమన్నా
Love you. ఐడి కార్డ్ మేడం మాకు కూడా ఐడి కార్డ్ ఇదే మాట్లాడతాం ఇదే నా క్రైమ్ బ్రహ్మనాయక్ గారు చేసినట్టు బ్రహ్మనాయక్ గారు ఇంకా జయనారాయణ చేయండి సార్. ఇంకెవరు రావండి? చాముండ్రావు నాగి గారు వచ్చారా? నాగి గారు